So last time, we had dealt with some function operations, and specifically we were focused on add, subtract, multiply, and divide, two functions. And we saw that when we added and subtracted and multiplied and divided functions, basically we just add, subtract, multiply, and divide the outputs of those functions. The only thing we have to watch out for is making sure the denominator is not zero when we divide two functions. And so we did that both with general variables, like if we plugged in an x, and we also said we could do that same thing with numerical values too. So when we plugged in a 3 or a 2 or a 5, and whatever. So we did that a couple of different ways. We also talked about multiplication by scalar, combinations of adding and subtracting and dividing functions. And so today what we're going to do is we're going to deal with function composition. This is our last operation, but probably one of the more important operations of functions, because this will also project into so this will project into what we do in section 1.7. All right. So function composition. When we want to compose two functions, we'll call them f and g. The composition of f with g, or composing f of g, means you plug in the output of g in as the input of f. And the notation we use is an open circle for function composition. So it means take the output of g and plug it in as the new input of f. One way to think of this is like a two-step process. We start with an input of x. We'll plug it into g first, and we'll get out some number or some value. And that number that we get out as the output of g gets plugged in into the f and gives us a new statement or a new value. So this is the idea of function composition. All right. One thing to watch out for is this notation. This is an open circle notation. Sometimes people, as they write it, or if they write it quickly, will put a small dot there, and then it may look like multiplication instead of composition. So just make sure you know which operation you're talking about in this case, in all cases. So let's take an example. We have f of x equals 3x minus 4, and g of x equals x squared minus 1. And we want to compose, I'll say, in both directions. We'll compose f of g of x, and then we'll do g of f of x. After we do that, we'll do that same process, but now instead of inputting the variable x, we'll input the variable 5, or we'll input the number 5 in for the variable. Be okay with that? So we'll do in general and then with the numerical value of 5. so g of f of x, the way I do this is I rewrite it to this notation. So this is a composition notation, but this is also a composition notation. F of g of x, it's like inputting g of x in for the input of x. And what that means, essentially, is I'm plugging in this x squared minus 1 into my function of f. Right? When we plug in something other than just a single variable like x, what we do is we replace the x here with this expression. So I take 3 times that expression and then subtract 4. And if I simplify that, I distribute 3 times x squared is 3x squared. I'll do 2 steps here. 3 times -1 is a -3, minus 4 is a -7. So we get 3x squared minus 7 as our final composition. Notice that the composition of 2 functions gives us another function. Right. Now, if you compose in the other direction, what you would do is you take the f of x and plug it in as the input for g. F of x is this expression here, 3x minus 4. So that's going to replace my variable in g. I'm going to take 3x minus 4, square that, and then subtract 1. Be careful when you square polynomials. Remember, that's not 3x squared minus 4 squared. Okay, you have to take 3x minus 4 times itself. So you would do 3x minus 4 times another copy of 3x minus 4. Okay, what I'm doing there. I'll simplify that fairly quickly. That will be 9x squared minus 12x minus another 12x plus 16 minus 1. That's what happens when you multiply that through. And so the final simplified answer would be 9x squared minus 24x plus 15. Okay. Notice that obviously these are 2 very different expressions. So that tells us that the order of composition is important. F of G is not the same thing as G of F. So be very careful when you do that. Now, just like when we were multiplying and adding and subtracting and all of that kind of stuff, if we wanted to do composition with numerical values, there's 2 ways to do it. Now that I have this expression, if I did f of g of 5, I could just plug in 5 into this expression and say 3 times 5 squared minus 7. I'll go ahead and do that over here. 3 times 5 squared minus 7. I think that's a 68, if I'm doing that right in my head. The other option, if I wanted to do that, is I think of where does G send the number 5? Plug in 5 squared minus 1, that's 25 minus 1, that's 24. Did I get that? So G sends 5 to 24. And then take that 24 as the output and make it as the input here. So 3 times 24 minus 4. 3 times 24 is 72, minus 4 is 68. Does that make sense? So that's the other option you can utilize. Okay. That option, that second option, is probably a little bit faster if you were just asked to compose G of f of 5. So now we're on this one. And you didn't want to take a lot of time doing this multiplication here. So you didn't want to do this multiplication. It might be faster to just plug into f first. And say if I plug in 5 into f, that's 3 times 5 minus 4, that gives me 11. And then plug in 11 into the G. 11 squared minus 1. 11 squared is 121 minus 1 is 120. Is that right? 120. So you could do that as well. Right? That's probably a little bit faster if you just had to find G of f of 5. Compared to multiplying the function expressions out, doing all that kind of work. Hopefully that makes sense. Good. There. So 2 options there for finding compositions with numerical values. You can find the composition with a variable x here, if you'd like. Or you can just trace the input-output process a couple of times. Okay. By the way, a good check would be to plug in 5 into this, just so that you can confirm G of f of 5 is that. If I plug in 9 times 5 squared, minus 24 times 5 plus 15. Sure enough, I got 120 again. Right? I plugged in that. I'll write it down. Plug it in there. I got 120. So that's a good confirmation that I've done both of these correctly. Both processes. So that's the idea of function composition. And like we said, in general, function composition is not commutative. The order in which you compose two functions matters. We saw that in this example, obviously. We can see that in most any example. There are a couple of exceptions, but they're kind of unique ones. So it's not commutative. F of G is not the same thing as G of F. I want you to do this example. We'll take f of x as the absolute value of x plus 3. And then g of x is x minus 9. And then we'll compose them in both directions. And then let's plug in a -7 as well. All right. This one should go a little bit quicker than the last one because we don't have to square a polynomial, if that makes sense. So I want you to compose in both directions and then plug in a -7 in the general and the specific. Okay. Go ahead and try that on your own. Take a few minutes. All right, so let's go ahead and do this. I'm going to do the f of g of x first. If I do that, basically, I'm going to be plugging in x minus 9 into the function f. So I'm replacing my variable in f with the expression x minus 9. That's going to give me absolute value of x minus 9 plus 3. So all of that inside of absolute value. So absolute value of the quantity x minus 9 plus 3. So that's going to give me, if I simplify that, the absolute value of x minus 6 when I combine like terms. On the other side, we're going to take g of f of x. So into the expression g, I'm going to put the absolute value of x plus 3. So I replace the variable in g with the absolute value of x plus 3. And in that case, I would have absolute value of x plus 3. And then outside of the absolute value, I would subtract 9. So both of these are absolute value functions, but this one would have been shifted to the right 6 units. This one would have been shifted left 3 units and then down 9 units. We're talking transformations. Be careful with that. You can't combine this 3 and this minus 9 because one of them's inside the absolute value, one of them's not. You should be combining both of these because both of those are inside the absolute value. Now, if you wanted to, you can plug in -7 into this. You can plug in -7 into this and figure out what that is, what each of those are. You can also do the tracing thing. That's what I'll write on the board. So f of g of -7. If I plug in -7 into g, -7 minus 9 gives me a -16. And if I plug in a -16 into my f, then -16 plus 3 gives me a -13. Absolute value of that is a +13. Okay, so if I did the G to F step-by-step process, I'd get that. I'd also have gotten a 13 if I plug in the -7 here as well, right? -7 minus 6 is -13. Absolute value of that is 13. So I get 13 either way. That's my point. Here, if I plug in a -7 into G of F, f of -7 plus 3 gives me a -4. Absolute value of that gives me a +4. So this is G of +4. And then 4 minus 9 is a -5. And again, if you did that same process, you plug in a -7 into this, got an output, you would also have gotten a -5. Any questions about that? Composition in general, and then plug in values in general. Okay. Now, so far, those first couple of problems, I gave the explicit outputs for the f of x and the g of x. In other words, I gave the expressions. And using those expressions, we found function composition in general, like with the general value for x. And we found it for specific values, like when we plugged in a 5 or plugged in a -7. Well, we don't always have to give an explicit expression to find function composition, because we can trace function composition. If we're trying to do f of g of x, we can see where g of x takes my variable x, or my number, what the output is, and then with that output, we can plug that output into f. So as long as we can find the outputs that I need to find, I can do function composition without the specific expressions for f of x and g of x. Let's do this numerically at first. And I'll write this on the board as we talk through this, because there's a lot of outputs that are given in this example. So it gives us a bunch of outputs right up front. It says, what if f sends 2 to 10, f sends 7 to 4, f sends 9 to 1, f sends 4 to 2, and then g sends 4 to 9, g sends 2 to 4, g sends 10 to 7. And then compute the following. Okay. I know there's a lot of examples, but if we do f of g of 4, and then f of g of 10, g of f of 4, g of f of 7, and g of f of 9. Okay, so I don't forget. So let's start out with g of f. No, let's start out with f of g of 4. Excuse me, this top left one. Right? We're going f of g of 4. So what we would do is we would take the function f and we plug in g of 4. And so we look back into our expression outputs here, and it says g sends 4 to 9. So we're getting f of 9 and f sends 9 to 1. That's it. That's the answer. if we compose f of g of 4, we get out the value of 1. Let's do the reverse. Let's do g of f of 4. I'll do the one on the lower left here, g of f of 4. What we would do is we'd start out by saying, where does f send the number 4? F sends the number 4 to 2. So f of 4 is 2. And then that becomes the input for g. So where does g send the number 2? Send it to 4. So interestingly enough, in that case, g of f of 4 is 4. Input of 4, give an output of 4. Try the other 3 on your own. F of g of 10, g of f of 7, g of f of 9. Using all of those input-output values at the top. All right, once you've seen this, it's not a crazy thing, although I always got to look back up and reference and that kind of stuff. So we had f of g of 4, we had g of f of 4. F of g of 10, I asked where g sends 10. That's what I do first. And it sends 10 to the number 7. And then I ask, where does f send 7? F sends 7 to 4. G of f of 7. We just saw that f sends 7 to 4. So we input the 4 into the g. G of 4 is 9, right? G of f of 9. F of 9 is an output of 1. Where does G send 1? You see on that slide? Didn't say, right? So right now, this would be undefined. Our slide did not tell us where G sent 1, so we don't know. And so that one's undoable at this stage. It might send, there might be some underlying function that we don't know, but at this stage, it's undefined. Okay. But there you go. Again, the way I think of it as just like a tracing, like if I'm doing F, let's do this one, F of G of 4, we're starting out with the input of 4, we're hitting it with G, we're getting an output of 9, and then we're taking that 9 and inputting that into my F function and getting an output of 1, right? So 4 goes to 9 goes to 1. And I'm talking about this, right? So if you think about it like that, then it's nice. And this kind of a thought process will set us up for the next section too, right? That's why I keep referencing back to that picture. Now you can do the same thing I did here, but with graphs as well. Thought I was doing that. Hopefully we all know how to read a graph. I know that. We just have to realize that right here, I'm using the left graph as my F of X, and my right-hand graph as my G of X. Be okay with that? So left-hand graph is F, right-hand graph is G. So if I'm doing G of F of 2, what I would start with is I'd start with the F of X and I'd plug in 2 into that. Notice that when you plug in an X value of 2, you should get an output value of -1. All right? Does that make sense? Can everybody read that? Might be far if you're sitting in the back of the room. But F sends 2 to -1. And then I say, well, where does G send -1? G sends -1 to -2. So therefore, G of F of 2 becomes a -2. And just based off the graphs. Let's do G of F of 6. So we start out with F of 6. F of 6 gives me an output of -1, or excuse me, of +1. F of 6 is a +1. And then I look at where +1 is sent with G, and since G goes to the point 1, -2, this is also sent to -2. So that also becomes a -2. All right, at G of F of 6 f of 6 becomes a positive 1. G of a positive 1 is a negative 2. Let's try this one. This one, we need to plug in 0 into the g function. Well, if I plug in 0 as my x value, my corresponding y value looks to be negative 3. So g of 0 is a negative 3. And so I plug that negative 3 into my function f. And when I plug in negative 3 into f, it looks like I get a negative 3.5. So plug in a negative 3, go down, you get about a negative 3.5 right there. So that last problem gives me a negative 3.5 as the output. So I got negative 2, then another negative 2, and then a negative 3.5. I probably should have kept the same colors, but I didn't. I want you to try these, or just this example. There's 3 questions on the bottom on your own. Here, the left-hand graph is the f of x, and the right-hand graph is the g of x. Okay. See what f of g of 2 is. G of f of 2, and then g of f of 1. Try to do that trace, trace through where we're taking. I guess I should do this. All right, so let's go f of g of 2. So you input 2 into g, that was the straight line. And it turns out you get out of 2. You input a 2, you get out of 2. So we're going to plug in f of 2. And when you plug in 2 into f, you end up getting a 4. Everybody else got that? 4. G of f of 2, well, f of 2 we already know is 4. Again, G is the straight line, so I look up the fact that the line goes to the point 4, 0, and therefore if we input a 4, we get out a 0. So, 0. If you input a 1 into your function f, you get out a 3. And then when you input a 3 into G, you get out a 1. By the way, notice that you input a 1, you got out a 1. Does that mean f of G is the identity? It's going to send every number to itself? Of course not, right? Doesn't send 2 to itself. It sends 2 to 0. Does send 1 to itself, but doesn't send other numbers to itself. You guys heard that term, the identity function? Good. Well, that's what we're going to use on the next section. When we talk about function inverses, and so let's start on that. By the way, that was the end of the function composition, function operations section. So function composition, function operations. Excuse me. Which was section 1-4. That's done. And now we're going to get started on the next section, which is inverse functions. And I bring that identity function up because that's the start of this section. Okay. The identity function is the function that whenever I input, I get the exact same output. So I input a 2, I get out a 2. I input a 1, I get out a 1. I input a 14, I get out a 14. I input pi, I get out pi. The identity function takes any x value as its input and has output of the x value. Now, it's called the identity function for 2 reasons. The first reason is you input something and you get back that something. I input a pi, I get out a pi. I input a 14, I get out a 14. I input a 1, I get out a 1. That's one understanding of the identity. The other interesting thing about the identity function is that under function composition, if I take f and I compose it with the identity function, I get back out the function f of x. Let's do f of the identity function first. That's f of the identity function, which we know the output of that is just x. So that's just f of x. On the other hand, if you do the identity function composed with f, you get the identity function, obviously input f of x, but the identity function just gives you the input out. So you're just getting the f of x out. So either way you compose the identity function, you just get f back, f of x back. So it's the identity function because it takes numbers to itself, but also because under function composition, you get back the original function. Now, this leads us to the concept of a function inverse. When we talk about a function inverse, we're talking about the inverse under function composition. So imagine I have a function f of x. If I compose it with a g of x, and I get back out the identity function, so I get back out just x. Then I say g is the inverse function of f. And we write the inverse function notation as f raised to the -1 power. Now, we have to be careful about that notation. F raised to the -1 power can mean a couple of different things. In this class, it'll always mean inverse function. If people are talking about the multiplicative inverse versus the inverse under composition, then we would write it in a different way. Okay, follow that? I'll write this on the board real quick. So just a quick note on notation. Whenever I write something in here, this is equal to the inverse of f. If somebody were to write something like this, they may be talking about 1 over f. We follow that? Usually we don't write it this way, but that's what. So just a quick note on that. You won't see this notation. I don't do any of that in this class, but just as a note. So this is the inverse function notation. This -1 exponent, it doesn't mean the same thing as like 5 raised to the -1. 5 raised to the -1 power is 1 over 5. Does that make sense? That's not what this means. This means inverse function under composition. So hopefully that makes sense. So f of -1 is the inverse function. Good. Now I want to point out something. If we're doing this tracking where we hit our function, all right, let's take our input x1. So that's a specific number input. And we get out a y value of 1. Then the inverse function, you'll have to put in a y value, y1, and get out that same x value, x1, that you started with. Now, what's that mean? Well, this means that if I have 2 different x values that are sent to y1, then the inverse function would not be a function, wouldn't be a well-defined. We follow that? So if I had an x1 and an x2 that was sent to this value of y1, then when I did the inverse function, I'd have 2 places for it to go, which is a problem. So in order to have an inverse function, we're forced to have f of x has only one x value for each y value. So that means if I want my f of x to actually have a proper inverse, it has to be a one-to-one function. So not only does it have to pass the vertical line test, it also has to pass the horizontal line test. We went over one-to-one functions a while back. Just recall that one-to-one functions means if the outputs are the same, then the inputs have to be the same. So in other words, a function passes the vertical line test. One-to-one functions also have to pass the horizontal line test. Now, this is not going to be a huge sticking point for this class. We'll see how we kind of can get around it in just a moment. But let's start out with determining which of these functions are one-to-one and which are not. So we have f of x equals 3x minus 4, g of x equals x squared minus 1, h of x equals absolute value of x plus 3, and k of x equals x minus 9. In this case, what I'll do is I'll just graph them, and we'll look at and decide using that vertical and horizontal line test. We all know that they're already functions because they're written in function notation, but 3x minus 4. That passes the vertical line test, so that's one-to-one. G of x equals x squared minus 1. Passes the vertical line test, but not the horizontal line test. I misspoke last time, didn't I? I said horizontal, I meant vertical and horizontal. So that first one, f of x equals 3x minus 4, obviously it passed the vertical line test, it was a function, but it also passed the horizontal line test. So it's one-to-one. X squared minus 1 passes the vertical line test, so it's a function. It does not pass the horizontal line test because I can draw a horizontal line through this and hit more than one spot. So it's not one-to-one. H of x was equal to absolute value of x. Oops, no, I forgot the numbers. What was that? X plus 3. Is that one-to-one or not? No, does not pass the horizontal line test. So this is not one-to-one. And then we said k of x is equal to x minus 9. That does pass the horizontal line test. So that is one-to-one over the entire real numbers. You can do this for others as well. Again, if you're doing this, just graph it. This time, I think I'll just graph it on the TI-84 calculator instead. We'll go y equals, and then graph x to the third minus 2x. And then I'll graph x to the third minus 4, and then 1 divided by x minus 3. I can project that up. Oh, yeah, that did. That's better. All right. So this is the first one. This is the x to the third minus 2x. If you look at, there's a horizontal line, specifically the x-axis, that crosses this graph in multiple places. So this is not one-to-one, fails the horizontal line test. Okay, that's the x to the third minus 2x. X to the third minus 4, if I graph that, I get this. Every horizontal line goes through that graph at just one spot. And therefore, this is one-to-one. So while x to the third minus 2x is not one-to-one, x to the third minus 4 is one-to-one. That's one of the tricky things about, cubic equations, that some of them are and some of them are not one-to-one. And then lastly, 1 over x minus 3. Make sure you put the x minus 3 in parentheses when you do that. Oh, should I not turn that on? No, I didn't turn that on. It's good. Weird thing. I get this. Now be careful here. This is a weird thing that your calculator does. My calculator did. It drew a connecting line down here to here. That's basically drawing a vertical asymptote. That line actually doesn't exist on the graph if you draw it by hand. That makes sense, that vertical line. Every horizontal line, if you ignore this, again, this asymptote that the graph drew, every horizontal line actually only goes through this graph one spot. Again, you have to kind of ignore that vertical one because of the way it graphs. So this is one-to-one. Even though on the TI-84 calculator we see this weird vertical line, I have to ignore that vertical line. That's just a product of how the calculator graphs things. It always connects dots. So it's plotting a bunch of dots and connecting those dots. And one of them went down here, and then the next one came up there, and so it connected those two dots.
So it's fine on this.
What's that?
It looks fine on this.
Yes, sometimes your calculator might not show that, depending on what operating system and what the specifications are and how it's graphing. But yeah, so for sure, there are some calculators that do not show that little vertical line. Good. Now, here's why I said in our class, it won't be a big deal if a function is not one-to-one, because if a function is not one-to-one over the entire real numbers, what we can do is we can restrict the domain we're using. And in our class, we're going to freely restrict the domain. So, for example, if you graphed f of x equals the quantity x minus 3 squared plus 5, it's not 1-to-1 over the real numbers. But if you look at it, where our domain starts in 3 and goes up to infinity, then it would be 1-to-1. So if we restricted the domain to just 3 to infinity, it would be 1-to-1. But get that? Was it plus 5? Can't remember. So here's the graph overall. Clearly does not pass the horizontal line test, so it's not 1-to-1 over the real numbers. But if I restrict the domain to just numbers bigger than or equal to 3, then it does pass the horizontal line test. So the question is, can we find an inverse? Well, we can find an inverse on this restricted domain. We can find a proper inverse on this restricted domain. But we can't find an inverse over the entirety of the real numbers. And just knowing that allows us to find inverses even when we're not dealing with the entirety of the real numbers as our inputs and outputs. Okay. I won't be really specific every time. Oftentimes I'll just say on an appropriate domain or on a valid domain, this is the inverse. Okay. We won't always, in fact, you won't be asked to specify which domain we're using. I will talk about as we kind of go through which domains we're using. But remember, the domain of the F is the range of the F inverse, and the range of the F is the domain of the F inverse. So it kind of gets tricky on how we restrict. But on restricted domains, or on appropriate domains, or on valid domains, we can find inverses. So even in an example like this one, we'll be able to find an inverse, and we'll just say we're just going to use from 3 to infinity. Or we're going to use an appropriate domain. Okay. So before we actually do the finding of the inverse, let's see how to algebraically check for inverses. If I want to see if F and G are inverses of each other, basically I'm just going to compose F of G and G of F. Remember, function composition is how we determine inverses. So if I want to figure out if two functions are inverses, I just have to compose them. If I compose them and I get out the identity function of x, then those two are inverses. If I get out anything else, then they're not inverses. So let's take a look at these two examples. We have f of x, which is equal to 5x minus 8, and g of x, which is equal to 0.2x plus 40. And then we have another example where we have 4 times the quantity x minus 2 raised to the 3rd power as my f, and my g as the cube root of the quantity 1/4 x plus 2. And we're going to check to see if these are inverses on appropriate domains. So if I wanted to check to see if these are inverses, what I would do is I would compose. I'll just use this notation for function composition. And so into f, we're going to put in 0.2x plus 40. So we go 5 times the quantity 0.2x plus 40 minus 8. That's going to give me 1x. That's nice. But then 40 times 5 is 200. Minus 8 is 192. So I get x plus 192. And this means G and F are not inverses, right? I just need the x. The plus 192 throws it off. And so these are not inverses. You could check the other way as well. You could do G composed with F, but I don't need to. Once I know that one way doesn't give me the identity, then I know they're not inverses. So you could check the other way as well and compose the other way, but we don't need to. Let's look at these two. So let's do, I'll do this way. G of f of x. So I got to plug in 4 times the quantity x minus 2 raised to the 3rd power into my function g. That's the 3rd root of 1/4 times this whole thing. One-fourth times 4 just gives me 1. And so I get the cube root of x minus 2 raised to the 3rd power plus 2. Is that the same thing as x? That is not. That is not the same thing as x. I'll just write not x. You have to cube this first and then add 2, and that's going to throw everything off, right? If we were to subtract 2 on the outside, then we might get cube root and cubes to cancel out. So this one is not not a pair of inverses either. Try these two on your own. See what happens in these cases. All right, so let me go through these examples, okay? I'll do f of g of x. So I'm just gonna do this in one shot. We're gonna plug this in to this function. So that's gonna be 2 times the quantity 0.5 x minus 6 plus 12. Okay with me doing that? And then when I distribute the 2, this is going to give me x minus 12 plus 12, which is just x. So I get x when I compose that way. Now, it's always a good strategy to say if you get x composing one way, it's always a good thing to check that if you compose it the other way, you also get x. Again, I'll skip an intermediate step. We're plugging in the 2x plus 12 into my g of x. And you also get x that way, right? 0.5 times 2 gives me 1x. 0.5 times 12 gives me 6. Minus 6 gives me 0. So both directions, we get function compositions. So function compositions that give us the identity. So f and g are inverses of each other. Another way to say that is G is equal to the inverse function of F, or F is equal to the inverse function of G. All of those statements mean the same thing. So that one, they are inverses. Here, what we would do is I'll plug in the same thing I did last time, 4x to the third minus 2 into my function g. And you might get excited here for a second, but then you realize there's a distributive property. That we can't overlook, right? So be careful about that. You get really excited and forget that you're plugging in the entirety of 4x to the third minus 2, rather than just plugging in 4x to the third and then subtracting 2. What you end up with is a cube root of x to the third minus a half plus 2 when I distribute. This is a cube root of x to the third plus 1.5, and that 1.5 is throwing me off, right? That is not x. If I didn't have 1.5, then it would be x, but it's not x. So here, once again, F and G are not inverses. Not inverses. Any questions about that? Yeah.
What did you do between the 2 parentheses 0.5x minus x plus 12 equals x and between the next one? Well, I don't see how you
Wait, to go from here to here?
Yeah, like how'd you get that?
No, so this is one option. I composed F with G on this line, and then I did it the other way. I composed G with F on this line.
Right, but how did you get just x out of that? I don't see just
Oh, here?
an item.
Oh, okay. 2 times 0.5 is just 1x. 2 times -6 is minus 12. And then I did a plus 12 on the end. And I just in my head did minus 12 plus 12 is 0. So I got that. On this one, 0.5 times 2 is 1. So I get 1x. 0.5 times 12 is a plus 6. And then a minus 6. And I did this in my head. I said, oh, plus 6 minus x is 0. So that's just x. So we have inverses and non-inverses. That first example, well, on this example, F and G were inverses. This example, F and G were not. Now, interestingly enough, I didn't worry about any domain restrictions on any of these in these first 4 examples because these were all one-to-one functions on the entirety of the real numbers. Cube roots and lines do that. On the next slide, I have a couple of examples where we will have to restrict the domain. Because we'll have quadratics and square roots and fourth roots and all that kind of stuff. These are not one-to-one functions. not all of them are one-to-one functions, excuse me, over the real numbers. I want you to try these two on your own. Don't worry too much about restricted domains. We'll talk about that at the end. But just decide if each of these pairs could be inverse functions of each other on some restricted domain. Okay. So would you get x for certain values of x through function composition? Yeah. All right, so let's take a look at these first two, and we'll do a function composition f of g of x. So I'm going to plug that in to here, or I could have done the reverse function composition, g of f of x. You have a preference or no? Doesn't matter. All right, so I'll do f of g of x. So this expression gets plugged into x, so we would take square root of x plus 9 and square it, and then subtract 9. Is that the same thing as x? No, it's not going to be x. It's not going to be x. Because of the way I have to square this, I have to think of this as square root of x plus 9 times another copy of square root of x plus 9. What would happen is you get essentially square root times square root gives you x over certain domains. And then I get square root of x times 9, another square root of x times 9, I get 18 square root of x's. Then 9 times 9 would be 81. Minus 9, and if I wanted to, 81 minus 9 is 72. Obviously not x, right? So, F and G are not inverses. Be careful about those things. I'm trying to give you ones that look like, you know, they may be inverses, obviously, but a lot of them are not. On these two, let's do our composition. Now, what I would do is I take this fourth root, and then raise that to the fourth power, and then subtract 5. What's the fourth root of x plus 5 raised to the fourth power? X plus 5, kind of. On certain domains, it's x plus 5. All right? On certain domains, that's x plus 5. And so we do get our x out on certain domains. Okay. As long as we have x plus 5 being positive. So technically, as long as the x value is -5 or above, then we're good to go. By the way, if you did this in reverse, if you did your function composition in reverse, we would do the fourth root of x to the fourth minus 5, and add 5. The minus 5 and the plus 5 would cancel each other out, and I would get a fourth root of x to the fourth, which, again, on certain domains is equal to x. Okay. On that one, x has to be 0 or above for that to work. And so F and G are inverses of each other on certain domains, on those restricted domains. You don't have to write the on certain domains like on the test or on homework or anything like that. I'm just being thorough. So this is how you can check for inverses. Just compose the two functions. I know we've done a lot of these function compositions. So we can check for inverses by function composition. But that's not going to be a very effective way to find function inverses. You don't want to just keep plugging in and checking and doing all that kind of stuff. So there's another way and this is what we're going to do now, to either check for inverses, but also in more general sense, find inverses. let's imagine I wanted to find the inverse of some given function f. If we go back to this mapping picture, f sends x1 to y1. What does the inverse function do? Well, it sends y1 back to x1. So that means if you look at a function f, if I want to find the inverse function, I reverse the roles of the x's and the y's. I reverse the inputs versus outputs in my f of x, and that will give me my f inverse, if it exists. Are we okay with that? So to find inverses, all we're going to do is reverse the roles of x and y. And that's pretty straightforward to do, as long as we have nice domains. So let's take a look at g of x, which is equal to 3x minus 7. And then this is an f of x that I saw earlier. This is the one of the third powers. 4 times x minus 2 raised to the third power. And let's use this idea of reversing the roles of x and y to find inverses. Now, these are both one-to-one functions, I believe, on all real numbers, so I don't have to worry about restricted domains here. If I did have to restrict the domain, then I restrict the domain. Okay. These two examples, I don't have to. So here's what we do. We take g of x and we swap the roles of x and y. So now my old output is my new input. And my old input, my new output. So I just take and swap the x and the y. And then I just solve that equation for y. I'll add 7 to both sides. I get x plus 7 is equal to 3y. Then I would divide both sides by 3. And here's how I'll write this: 1/3 x plus 7 over 3 is equal to y. Now I have it solved for y. So what that tells me is that G inverse is such that the output of G inverse should be 1/3 x plus 7/3. Typically, I like writing the y or the output on the left-hand side. That's what it is. And you can check this if you want. Now, this is the final answer. We're just asked to find the inverse. So that's the final answer. I think I did that right. But you can check that by doing a composition. You had a question, though.
Would it be alright if instead of like split them up into 2, if it was just like divided by 3?
Oh yeah, that'd be equivalent. Yep. So like x plus 7 all divided by 3. Yeah. Yep, that'd be equivalent. And Moodle should recognize both of those as being the same when you type that. If it doesn't, let me. All right. Oh, yeah, so you could check, let me just check what I think. Is the inverse. I'll do this pretty quick. So I take 3 and then input 1/3 x plus 7/3, and then subtract the 7. 3 times 1/3 x is just x, 3 times 7. Sure enough, when I compose g with what I just found, I get the identity function. And if you did it the other way as well, if you did g inverse composed with g, you'd also get the identity function. I won't go through that. Okay. All right, so let's do the second one. This is one we came across earlier, and we were trying to check if this and some other g were inverses of each other. Let's actually find the inverse. So we're going to swap the roles of x and y, and then solve for y. I'll just write that over here. So the first thing I would do is divide both sides by 4. I can leave that as x over 4, or I can write it as 1/4 times x, doesn't really matter. In order to undo a third power, I would take a third root. So we're going to take third root of both sides. Which gives me the third root of 1/4 x is equal to y minus 2. And then I'd add 2 to both sides. When you add 2, make sure it's not underneath the square root, apart from the square root. So we're getting the third root of 1/4 times x. And then plus 2 is equal to y. And this means the inverse function is this expression of third root of 1/4 x. And then outside of that root is a plus 2. If you get very comfortable at doing this, then you can do those other questions that we just got done, like saying, is this the inverse of this? By just finding the inverse, I could have found the inverse of f of x, and then said, yeah, that's not the same thing as what g was. So if you get really good at this process, of swapping x and y, then solving for y, then you can do all those other ones by just saying, well, I know what the inverse is g the inverse? What's that? The inverse what? Let me do one more. I'll look at this h of x, which is 5 times the square root of x plus 3 minus 8. And I'll find the inverse for that one. And then K of X, I'll write these, the K and the P down. I'll have you guys do those in a second. Sorry. Erase this. So K of X is equal to the quantity X minus 10, all raised to the 2/3 power. And then P of X is equal to negative X squared and then minus 5. And it says find the inverse function of each of these on some appropriate domain. Okay. So we'll swap X and Y on this H of X. And then we'll solve for Y, just like we've been doing. So the first thing that I would do to solve for Y is add 8. That is add 8 to both sides. Then I would divide both sides by 5. I get 1/5 X plus 8/5 is equal to the square root of Y plus 3. If you want to use decimals, that's fine too. .2 and 1.6 for decimals. Now, at this stage, we have a square root. In order to get rid of a square root, I would square both sides. And we have 1/5 X plus 8/5 quantity squared is equal to Y plus 3. Kind of. You guys know what I mean by kind of?
Yeah.
For certain values of Y, that'll work. Okay. For certain values of Y, that'll work. And that's on the appropriate domain version. Okay. And then subtract 3. So I end up getting, well, let me write it here. 1/5 X plus 8/5 quantity squared minus 3 is equal to Y. And this means my function's inverse, H inverse, is that 1/5 X plus 8/5 squared minus 3. That's the inverse of H on certain domains. Okay. So with certain domains and ranges, those two things will be inverses. Notice how, again, I'm not being too specific about which domains and things like that. Essentially, I'm assuming this Y plus 3 has to be a positive. In this process of doing the squared, going back and forth here, squared versus square root. I needed this to be a positive. And I also needed this to be a positive too. Just the 1/5 X. I wanted a positive underneath, I wanted a positive over here. Everything's positive. Okay with that? By the way, if I ask you, instead of using fractions, to use decimals, that's pretty straightforward. 1/5 is just 0.2. And 8/5 is 1.6. So if you'd rather use decimals, you can use that too. I like leaving things as fractions unless the question asks me to put in as decimals. All right. So I want you to try the K of X and the P of X on your own. Try to find inverses of that. And again, when you use appropriate domains, just assume things are nice and positive numbers so that when you do square roots, you get real numbers. So that when you square things and take square roots, you get nice positive values.
Is that supposed to be to the 2/3 power, or is that just times 2/3
What's that?
on Canada?
That's to the 2/3 power. Yeah. So the exponent is 2/3. The exponent is 2/3. All right. So I think everybody is like, look, has a general idea what we're doing. So let's go through and solve. In order to get rid of a 2/3 power, I would raise both sides to the 3/2 power. Okay, so I'd raise both sides to the 3/2 power. And so I get x raised to the 3/2 power is equal to y minus 10 raised to the first power. By the way, again, when you do that, you have to be careful about the values of y and the values of x we're taking on. Otherwise, strange things can happen. So this is on some restricted domain. And then just add 10 to both sides. So we get x raised to the 3/2 power plus 10 is equal to y, which means the inverse function of k of x is x raised to the 3/2 power, then plus 10. That's it. That's the whole thing. If you wanted to check, you could do function composition and see that it works. Again, it does work. There are some restricted domain issues that we're dealing with. Similarly, on the second one, P of x, I would add 5 to both sides. Then divide everything by a -1. That would give me -x minus 5 is equal to y squared. In order to get rid of y squared, I'd take a 1/2 power to both sides or a square root to both sides. Doesn't matter how you write that. So I'll take a square root of both sides. And again, in that step, there's some restricted domain stuff. Technically, you could have taken a negative square root on this side. Whenever you're doing the square roots or the third powers, let's just always take the positive one so everybody's on the same page. That makes sense? We'll take positive square roots, or if you took a 4th root, you take a positive 4th root. Or like over here, we took a 3/2 power. We didn't try to do a negative 3/2 power, anything like that. Okay. So we'll do positive square roots on everything that we do, or positive domain restrictions. If we do that, then I end up with the inverse function of P is the square root of -x minus 5. That -x minus 5 is all underneath the square root. I could also have written that as -x minus 5 raised to the 1/2 power. There's the answer. So the general concept of finding function inverses is fairly straightforward. We swap x and y, and then we solve for y. Sometimes when we solve for y, we have to worry about, restricted domains. Again, in this class, we're not going to have to write out which domains, because again, the domain of P is the range of P inverse. Domain of P inverse is the range of P. So on certain domains and ranges, those will be inverses. Okay. That's all we'll say. So lastly, what I want to do, since we all kind of get the general gist, is I want to go over a couple of solving techniques that can make our lives a little bit weird. Okay. Let's take a couple of functions and find the inverses on whatever restricted domains we need. These two take a little bit, how do I want to say, a little bit more clever solving techniques. Not too crazy on these two. We'll see two more on the next slide that also take some clever solving techniques, but Clever domain restrictions. But I just want to show you these techniques, is what I'm trying to get at. Okay? So I want to show you the techniques that these two would take to find function inverses. The solving techniques for y is the important part. So as usual, we're going to swap the x and the y. And we get x is equal to 5 divided by y minus 4. Okay, now my first step, what should I do first step?
Times by positive 4.
Not quite. You're,
Multiply by 5. 5 over negative.
what I would do is I would multiply both sides by the denominator and get rid of the dom. If I do that on the left-hand side, I'm going to distribute the x times both the y and the minus 4. You could also think of this as cross multiplication. Think of this as x over 1 and then cross multiply. That's the same process. If I do that, I get x times y minus 4x is equal to 5. So the y minus 4s will cancel each other out. And you'll just be left with the 5 on the right-hand side. Again, if you do cross multiplication, you get the exact same thing. Now I want to solve for y. So what I would do, since this 4x is a term without any y in it, I would add both 4x to both sides. I get x times y is equal to 4x plus 5 or 5 plus 4x, doesn't matter which way you write it. And then to solve for y, I simply need to divide both sides by x. So I get y is equal to 4x plus 5, all divided by x. You can rewrite that if you'd like to, it doesn't matter, but I'll leave it like that. Okay? You could, if you wanted to, say 4x over x is 4, 5 over x is 5 over x. But there you go. So what we're getting is that the inverse function of f here is 4x plus 5 multiplied by x. Or some algebraic equivalent to that. Go ahead and try g of x on your own. Take a couple of minutes to try that. It's very, very similar. Although we have an x squared instead of just an x in the denominator, but that should be, again, fairly straightforward. All right, hopefully we do this. So we swap x and y, multiply both sides by that denominator, that'll clear it out. That's the same thing as again cross multiplication. If I do that on the left-hand side, when I distribute the x, x times y squared is x times y squared, or y squared times x, you can write that either way. And then 5 times x is 5x. On the right-hand side, the denominator cancels out, so we're just left with the 7. I would subtract 5x on both sides. Doesn't matter the order you write this. If you write this as 7 minus 5x or negative 5x plus 7, yeah, it doesn't matter that order. Then I would divide by x. I get y squared is equal to negative 5x plus 7, all divided by x, or an algebraic equivalent of that. Divide it into 2 terms if you'd like. And then in order to get rid of the square, in the same way we did last time, I'll take a positive square root of both sides. And if I do that, I get y is equal to the positive square root, or the positive, could have also done a 1/2 power of negative 5x plus 7 divided by x. And that means the inverse function of g is the square root of a fraction whose numerator is negative 5x plus 7 and whose denominator is x, or some algebraic equivalent of that expression. Again, there is quite a few different places that we would have had to restrict the domain. When we took those positive square roots, we were assuming positive things on both sides, essentially. And also, there's a couple of times where we divide by x, so we'd have to restrict the domain. We couldn't have 0 as x either, if that makes sense. Because we divided by, wouldn't want to be able to divide by 0. So, a couple of different domain restrictions in there, but the overarching idea is pretty straightforward, I hope. All right, this will be the last example in this section. Let me pull this down so you can see it. Same thing, we're going to find the inverse. This one, I'll just kind of go through it, go through the process. F of x is equal to a fraction whose numerator is 2x minus 6 divided by 3x plus 4. So here we have 2 x's in there. That's the trick. And then g of x is equal to the absolute value of x plus 13, and then minus 5. And again, we're looking for inverse functions. All right, this one's the trickier one. So let me do that first. We're gonna swap x and y. Write that down, swap. X, y. I have to. Anyway. So swap x and y, and in the same way we did in the previous two examples, we're going to multiply both sides by the denominator. So to get rid of the denominator, I would multiply both sides by 3y plus 4. Should have wrote that close, I guess. But multiply both sides by 3y plus 4, and then I'll distribute. I get 3xy plus 4x is equal to, on the right-hand side, this will be 2y minus 6. Anybody know how I solved this for y? Go for it.
What I did is that you could just add the 6 to the other side, then divide the y, and divide the 2.
Right. Not quite. I think if you divide y, you're going to get more y's in there than you want. What, in this case, the way that I would solve it is I would get all of the terms with y's on one side and all the terms without them on the other, and then factor out the y. Okay. In this case, we can do that. Let's subtract 2y from both sides. And then I'll get rid of this 4x as well. So I'll subtract 4x from both sides. We'll end up with 3x times y minus 2y is equal to negative 4x minus 6. And then, I'll write it up here, on that left-hand side, we'll factor out a y. And then what we can do is divide both sides by 3x minus 2. But you have to divide it as a quantity, as a single quantity. You can't divide by 3x and then divide by 2. You have to divide that by a whole expression, 3x minus 2. So what we get is y is equal to a fraction whose numerator is negative 4x minus 6 and whose denominator is 3x minus 2. And that's what the inverse function of f is. Be okay with that? So we get the y's on one side, everything else on the other. I'll go through this one real quick. Probably going to take me a minute. You can just watch if you want. What I would do is swap x and y. Then we'd add 5 to both sides. And then we'd restrict the domain. We'd say, we'll assume everything's positive. If we assume everything is positive, then we can just drop the absolute value sign. Like on the restricted domain, we assume everything's positive, drop the absolute value sign, and then subtract 13. And we get x minus 8 is equal to y on whatever restricted domain we're on. Okay. And so x minus 8 on that restricted domain. Is that right? if you wanted to do it on the other, if you wanted to assume that this was a negative, then you could assume that negative too, but we'll always assume positive stuff, nice positive. Okay. All right, well, we're done with this section. I do want to mention that while we solve these, there are certain functions that are very, very hard to solve. Okay, so not every time is it a real easy thing to solve. Here, you're going to be given, in this class, you'll be given things that you can solve. Sometimes they'll take some clever work, but there'll be things that you can solve fairly straightforward. Okay? All right, I'll see you all next time.